Good afternoon, everyone. I would like to articulate my thanks to Dr. Ashwani Jain sir for giving me the opportunity to present the seminar on the topic geosynthetic testing techniques. The content will be as follows: introduction, type of geosynthetic products, function of geosynthetics, mechanism, need for testing, collection of test samples, identification of test samples, properties of geosynthetics, discussion of mechanical tests will be including wide width tensile test and CVR puncture test, and then the references. Since the last 4 decades, geosynthetics products have helped geotechnical engineers and contractors to solve several types of engineering problems where the use of conventional construction material would be restricted or considerably more expensive. The types of the geosynthetic products are as follows. The very first is the geotextiles, then geogrids, geonets, geomembranes, prefabricated vertical drains, geosynthetic clay liners, geocells, reconfinement, geobags, geotube, geocomposite, and geoothers. Common type of geosynthetic used for soil reinforcement include geotextiles. These are particularly woven geotextiles, geogrids, and geocells. Talking about the geotextiles, these are continuous sheets of woven, non-woven knitted or stitch bonded fibers or yarns. Geogrids have a uniform distributed array of aperture between their longitudinal and transverse element. A wide variety of geosynthetics product can be used in environmental protection projects, including geomembranes, geosynthetic clay liners, GCL, geonets, geocomposite, and geopipes. Geomembranes are the continuous flexible sheets manufactured from one or more synthetic material. They are relatively impermeable and are used as liners for fluid or gas contaminant and as vapor barriers. The main and exciting reason for exploring this product in the civil engineering is because of their excellent properties, which are enlisted as testing behavior, good flexibility, filtration characteristic, high water permeability, mechanical properties, can be welded together, does not form byproducts. They provide high resistance to climatic conditions, high resistance to chemical as well as biological attacks, chemical ultraviolet stabilized. And the main and exciting reason is that they help us to aid in rapid construction and reducing the time and the cost. They are environment friendly, sustainability and durability. Now we'll be talking about the functions of the geosynthetics. Separations. This function prevents the intermixing of soil types of different size to maintain integrity of each material while allowing free passage of liquid and gases. Drainage collects and conveys, allows fluid and gases to flow through the plane of the material, facilitates surface water runoff. Filtration allows to restrain soil or aggregate subject to hydraulic forces. This function is often partnered with the separation. Barrier isolates one material from one another. Common application are landfills, lagoons, or other holding ponds, where necessary to prevent contamination of surrounding area. The next is the reinforcement, which provide additional strength to soil and aggregate. Protection prevents acute damage caused by adjacent materials, often used in concert with a barrier to ensure surrounding areas will not be contaminated. In this picture, this is the illustration of these previous geotextile geosynthetic products and the various functions which are being performed. This is the landfill site. The multiple use of geosynthetic in the design of modern municipal solid waste landfills is a good illustration of an application in which the different geosynthetics can be and have been used to perform all the functions discussed previously. Now, talking about the mechanism, we will take a now talking about the mechanism, how these are being installed. We will take a tank and fill it with a dry sand. When we remove the side AB as shown here, the vertical face of the sand does not remain stable and the soil mass rearranges itself. But if we fill the same tank by providing layers and folding these geotextiles, and when we remove this side AB, there may be some bulging, but the face remains vertical and stable. This is so because when the soil particles in the failure zone begin to collapse, the geotextile reinforcement prevents the movement. Now the need for testing. We may not be able to identify the type of polymer or the type of material and so on, and we need to do the testing, and then of course for selecting a suitable material based on the design design and based on the design specification regulation, we need to select a product, and even for that we need to test a given number of products and then select a suitable material that is good for our construction works. Then during the manufacturing process, we need to do the quality control and frequently collect samples from the production lots and to do the testing just to make sure that the finished products has the properties which is meant for. We collect the samples at different rates and to do the testing, that is called quality assurance. The collection of test samples is done accordingly the code mentioned here, the ASTM D4354, ISO 354, ISO 9862 or Indian Standard 14706. During the production stage, test samples are collected at a uniform intervals for quality control purposes. During the construction also, test samples are collected at a specified rate. Number of specimens to be tested is given in respective standards. Now the next is the identification of the test samples. The grade of the material in terms of either the strength or the thickness or so on, and then the roll number, especially when it is the manufacturing stage, we need to know the roll number and then the date and time of the sampling. The sample shall be kept in a dry and dark place to prevent it from physical damage. Samples should be packed properly during shipping to the testing laboratories during the production stages. Now we'll be covering the properties of geosynthetics. Here are the mentioned properties. The first is the physical, mechanical, hydraulic properties, and then the endurance properties. The physical properties, they are fundamental properties that describe the material itself, and then the mechanical properties, they define the strength. They define the strength of the product and then its interaction with some other materials like soil or stones and so on. Then coming next to the hydraulic properties. These properties, they describe how they can allow the water to flow to the geotextile or flow across the geotextile. Then the endurance properties, when these geosynthetics applied in the soil, how do they last or how do they endure during the service life. Now the test on the geosynthetics are conducted in two ways. The very first test, it's being conducted directly on geosynthetics, and the second is that along with the site specific condition we use to test on geosynthetics. Now coming to the mechanical test that I will be covering, the very first will be the tensile test, which will be conducted by the wide width strip method, and the second will be the CBR puncture test. Standard test method for tensile properties of geotextile by wide width strip method. The apparatus and reagent required will be as follows. According to the ASTM, the tensile testing machine will be like this, here as shown in the figure, and the clamps of various types, area measuring devices, distilled water, and non-ionic wetting reagents for wet specimen. As I've discussed the clamp, these clamps may be modified to provide greater ease and the speed of the clamping in any event. caution must be taken to ensure that the type of material and the dimension of the clamp are adequate for the user expected fabric strength, size of jaw faces. Each clamp have few jaw faces measuring wider than the width of the specimen, that is 8 inch, and a minimum 50 mm 2 inch length in the direction of the applied forces. Here is the roller clamp on which your textiles will be covered or they will be installed. Now the test will be performed by first selecting the test specimen, sampling, that is sampling, conditioning and procedure, number of specimen, test specimen size. Prepare each finished specimen, that is 200 mm or 8 inch wide by at least 200 mm 8 inch long, with the length dimension being designated and accurately parallel to the direction for which the tensile strength is being measured. If necessary, centrally draw two lines running the full width of the specimen accurately perpendicular to the length dimension and separated by 100 mm or 4 inch to designate the gauge area. For some woven geotextile, it may necessarily to cut the each specimen by 210 8.5 inch wide and then remove an equal number of yarns from each side to obtain 200 mm 8 inch. This helps the maintain specimen integrity during the test. Now the conditioning is being done to provide the site conditions. Bring the specimen to the moisture equilibrium in the atmosphere for testing geotextile. Specimen to be tested in the wet condition shall be immersed in water and maintained at a temperature rate of 21 degrees Celsius. Now procedure here is covered as follows. A relatively wide specimen is gripped across its entire width in a clamp of a constant rate of extension. After conditioning a wet specimen, we will set machine rate at 10 plus minus 3% rates per minute. When we are done with clamping with our sample. And after that, apply a longitudinal force to the specimen until the specimen ruptures. Tensile strength, elongation, initial and secant modulus and breaking toughness of the test specimen can be calculated from machine scales, dials, recording charts or an interface computers. This picture is showing the test samples, dimension and how the force is being acted on it. On bottom left side, you can see the pictures before and after test of non-woven geotextile, how the geotextile has been performed without elongation and after elongation, these samples. And on the right hand side, you can see this is the woven geotextile, how before the test it was in a simple state and after elongation it got ruptured. There are markings you can see in between. A single line is being drawn and on these markings. Based on these we will be calculation. The tensile strength will be calculated by using this formula. The tensile strength is directly based upon the breaking force and the specimen width. And elongation will be calculated using this formula, which will be dependent upon these parameters, as you can see. Now, only if required or asked by the manufacturer, we will calculate the tensile modulus, which will be initial tensile modulus, offset tensile modulus and secant tensile modulus. These modulus are being calculated by using this equation and plotting on the graph. We will be drawing the straight line like this, which will be joining the first point of the straight line. And breaking toughness is also calculated only if it's asked. Breaking toughness is calculated depending upon the specimen we are using. If we are using an XY recorder, then we will be using the equation 8. And if we are using an automatic area measuring equipment, then we'll be going through the equation 9. Or if we are using manually obtained strain measurement criteria, then we'll be using equation 10. Now, the graph here is drawn between the tensile stresses and strain rate that we have provided. As you can see, on the x-axis we have the strain, and on the y-axis we have loaded in the kilonewton per meter. The A and C corresponds to woven geotextile, which exhibit very large strength and typically at a low strain develop the peak load at about 15 to 20% strain rate. This D and E are non-woven, heat bonded and needle punched fabrics. They develop their peak load at a very large strain. Here, in this case, about 70 to 80% strain, and comparatively their strength is much lower than the strength of woven geotextile. Now we will be preparing the final report, in which we will be calculating the average breaking forces, average elongation at specified force in percent, and if requested the average initial tensile second modulus as discussed. If requested the average breaking toughness, and we will be specifying the condition, either it is dry or wet. The size of jaw face is full scale force range used for testing. The next is the CBR puncture resistance test. Though, as we have seen, these geotextile materials are being laid and they have to encounter various type of stones. They might be blunt or sharp ones. Depending upon the type, we used to conduct the test, but mostly CBR plunger test is being used. CBR plunger test with a flat base. As you can see here, the CBR plunger test, there is an elongation, and this is the cone test for pinpointed stones. This test method can simulate the stress in the geosynthetics when rock fallen. The apparatus required and testing condition will be according to the ASTM D6241. Here is the ASTM testing machine and plunger with a flat of 50 mm. This is the CBR. This is the plunger. You can see with a flat of with a dia of 50 mm and clamping apparatus with internal dia of 150 mm. And the compression speed provided will be 50 mm per minute. The lab temperature will be set at to 21 degree plus minus 2 degree Celsius. Before concluding the test, I would like to enlist the material tested, sampling done, and how the procedure is being carried. The material tested mainly include the woven and non-woven geotextiles of different material depending upon their mass per unit area. They are polypropylene and polyvinyl chloride, needle punched and melt bonded, or silt film polypropylene. These are these material. Now sampling. Samples were taken neither closer than 6 inch because as you know 150 mm is the dia of the clamp, so we have to take the sample of at least 6 inch. Now cut the sample diagonally of the whole sheet. We will be selecting randomly one roll of geosynthetics, and along the diagonal of that we will be cutting the specimen. As you can see in these pictures, we have done the markings, but you can see these folded areas are being avoided, and especially in the case of woven geotextiles, what we do is we apply a thin layer of glue, as woven geotextiles are on the high chances to lose their fabrics, so we provide a thin layer of glue. Now coming to the procedure, first select the load range of testing machine such that rupture occurs at 10 to 90% of full scale load. Then center and secure the test specimen in the clamping apparatus. Test at the speed of 50 mm per minute until the specimen rupture completely. The maximum force is recorded as a puncture resistance. Then the average puncture strength is calculated and is reported as a puncture strength of the geosynthetic material. Here the fabric elongation is being calculated by using this formula, which is being given by Western German. In this equation, what is being done is A is the actual length from puncture to the clamp ring, and X is the elongated. Now we will be finding the elongation rate by change in the elongation. Change in elongation by dividing with the actual length of the specimen. And here is the graph between the plunger displacement to the fabric elongation. But there was a error, as we were not including this plunger base. Yes, this plunger base is having maximum elongation. So now the better formula is here. In denominator, we have added the radius of this plunger. But Kojofi noted that the elongation was not only on one side, it was acting on the periphery all along the surface, that you can call as a frustum. Now he has included the surface area of the frustum and also the base area on which the maximum elongation is being taken. We have given the equation number 4. Kojofi also proposed the following empirical equation as a correlation between the breaking force of the CBR test and the wide width tensile strength test, what we have conducted before for isotropic non-woven geotextile. This is an empirical formula which is dependent upon the tensile force and the puncture breaking force. The very first equation has given this report, and the second one has accounted this elongation, and by 3.4 we founded this elongation. Equation number 4 is considered to give an adequate representation of actual behavior, as maximum elongation was being calculated and accuracy. For woven materials, the CBR puncture load at failure ranged from 693 lbs to 762 lbs with an average of 733 lbs and coefficient of variation equal to 2.8%. For non-woven materials, the CBR puncture load at a failure range from 324 lbs to 457 lbs with an average of 362 lbs and coefficient of variation of 11.4%. Though woven geotextile exhibited a CBR puncture strength approximately double that of the non-woven material with the same mass per unit area, a finding consistent with the industry standards. The freeze-thaw conditioning showed minor levels of degradation on the puncture test. However, UV and weathering tests showed significant degradation in the puncture strength after exposure. Here is the references. I have taken the references mainly from this geosynthetic book by Robert M. Corner and various research briefs that I have found from ResearchGate sites and the ASTM codes and also various courses from NPTEL has helped me to cover these slides on mechanical tests, that is tensile weight test and CBR punches test. Thank you.